Hello everyone, welcome to my video on the area problem. So Calculus 2 is basically created trying to answer this question here. So in physics there's actually an equivalent question which involves the distance traveled by a vehicle, and it turns out the same special limit is required to solve both problems. Okay, so we're going to focus on the area problem. So what's the area problem? So we know how to find the area of regular shapes like a square, rectangle, triangle, polygons. But the question becomes now, how do we find the area of a rectangle? Let's say we have a rectangle over here where one of the sides is curved. It's not straight anymore. So if I remove this line over here and we make it so that the line becomes curved, how do I solve for the area of this shape now? This is the question. You may have some ideas. Maybe we could cut them into shapes, use maybe semicircles or remove a semicircle over here, something creative. These are all good attempts, but what Riemann decided to do, and it turns out it works out pretty well, is he decided to think of this as a function. So if we have our Cartesian plane, this is the x-axis, this is the y-axis, notice this is essentially a function. We could think of it as a function. And what we're going to do is we're going to approximate the area under the curve here. So the area of the shape, let's call it S in black. We'll call it A. The area under the curve. And the way we do it is we create small little rectangles approximating this area. So we'll create these little rectangles. I'm going to do it in red so that they approximate the area under the curve. And this is the idea. And we're going to make it so that the length of each rectangle is the same. And by doing this, we are approximating the area of the rectangle which has a curved side. Notice that the rectangles aren't perfect. There's some regions over here, it might be small, but these regions here are empty. There's holes. And sometimes you can notice that the rectangles actually surpass the function. Okay, so this isn't 100% accurate, but if we make the rectangles as skinny as possible, as small as possible, or as thin as possible, notice that the error becomes essentially very small, that it becomes negligible. Okay, so this is the idea of what we're going to do to solve or to answer this type of problem. Let's go ahead and look at some examples. So let's take a look at this example over here to see why taking a random shape and splitting it up or partitioning it into smaller rectangles is a good idea. So over here it's asking us to estimate the area under the curve of the function y equals x cubed on the interval 0 to 1. So let's begin by sketching the function. So we have our Cartesian plane, x-axis, y-axis. We have our function x cubed on the interval from 0 to 1. So the 0 is over here, let's say 1's over here. And the cubic function looks something like this. Okay. So as you can see, it's essentially the area that we care about, or the area under the curve, is this essentially a triangle with one of the sides curved, so not straight. So we have to find the area in this region here. Let's call it A. So the first thing we could do is notice that this area falls in this box here. Okay. So we definitely know that this square here, created by this dotted line and this dotted line, this square over here of side length 1, and this is also 1, we know that the area A over here underneath the curve has to be at least smaller than 1. So bigger than 0, smaller than 1. So by creating, let's say, a big rectangle over here, we can deduce the fact that the area is between 0 and 1. Okay, that's not that impressive. We could do better than that. Let's go ahead and try to improve on this notion. How do we do that? Well, let's make smaller rectangles. So if we, instead of taking a rectangle of size length 1, whose width is 1, let's take a width of a half. And by doing this, we actually have two methods of doing it. We have something that's called the left end point, and we have something called the right end point. Let's take a look at both these cases. Using the same image, I'm just going to draw two of them. Okay, so here we have our two functions. Let's apply the left endpoint and the right endpoint. So what we said is that we're going to divide it, we're going to partition it in two rectangles using widths of a half instead of one. So if we're using the left endpoint, that means that the left endpoint of our rectangle is going to touch the function. So the function here in green is represented by f of x equals x cubed. If the left endpoint touches the function, at 0, notice that we're going to have essentially just a small rectangle like this, right? And because the left endpoint has to hit the function, since the function here and the left endpoint at 0 starts at 0, the height of this guy is 0. So it's essentially not there. And then the next rectangle that we draw is at a half, and the left endpoint is going to hit the function here. So we're left with this region here. So this is the left endpoint. We created two rectangles where the left endpoints of the rectangles hits the function. Okay, let's take a look at this one. Now we're looking at the right endpoints. The right endpoints now, from 0 to half, the right endpoint of this triangle, of this rectangle, is going to hit the function over here, giving us this region. And again over here, between a half and 1, this red rectangle here is going to hit the function. The top right part of the rectangles are going to hit the functions. Okay. So our first estimations claim that the area has to be between 0 and 1. We said we could do better. By making the widths of the rectangle smaller, what could we conclude? Well, the area over here, notice that when we did the left hand point, we got an underestimation. This area here, the red area, is definitely smaller than what we'd expect the actual answer to be. The actual green area over here, the area under the curve, the whole thing would definitely be bigger than this area here. But what's the area of the red section? Well, we could figure this out. We know that the height of this region here is 0 and the width is a half. So finding the area from the left hand point, let's call it area L for now. The first rectangle essentially is its length times width, so 0 times a half, plus here, what's the height? We have to go ahead and find the height. How do we find the height? Well, we know that the height is essentially the y value when x is a half. This is the height, because that's when it hits the function at a half. So what we have is f of a half times the distance from a half to 1 is a half. The width of the rectangle is a half. So we have to plug in f 1/2 into the function f. So on the side, we know that f of x is equal to x cubed. This means that f of a half is equal to a half cubed, which is equal to 1/8. So this is really saying that we have 0 times a half is 0. F of a half is an eighth times a half, which is 1/16. So the underestimation is 1/16, which is a better underestimation than what we had previously when we said the lowest possible value is 0. Well, now we increased it slightly. Now the lowest possible value we could have is 1/16. So this is a better approximation. And notice that the left hand point in this example here is an underestimation. This isn't always the case. You might have a function that decreasing. Here the function is increasing. From left to right it's getting larger. So it's an increasing function, so the left endpoint happens to be an underestimation. But if the function was decreasing, you would have an overestimation. So left endpoints are not always associated with underestimation, so just be careful for that. So in this specific case, it's an underestimation of 1/16. Let's take a look at the right endpoint and see what we get as a value. So again, to find the area in red over here, so let's call it AR, area of the right region, the right endpoint. The first rectangle is a width of a half, and the height, so 1/2 is the width, and the height is f of a half. This is actually what we just saw here, f of a half. Plus, over here, the width of the rectangle is a half, and the height now goes up to here. So we know the height of this rectangle is f of 1. So to solve this, a half times f of a half, we know that f of a half is an eighth, because it's the same function, is 1/8, plus a half times f of 1. Well, f of 1, let's do this on the side. F of 1 again, we're plugging 1 into 1 cubed because the function that we're using is x cubed. So 1 cubed is just 1. So the height of the function here is 1, as was written here. So what we have here is a half times an eighth, which is a 16th, plus a half times 1, which is a half. Finding a common denominator here, we get 8 on 16. I'm just going to write it because I don't have the room. 8 on 16, which turns out to be 9 on 16. So instead of 1, now our estimation after splitting it, making the rectangle smaller, is 1 on 16. We know the area has to be between 1 on 16 and 9 on 16. So notice as the widths get smaller, our answer gets more and more accurate. Let's go ahead and subdivide these into quarters now. So now we're dividing them, or we're partitioning the, let's say the interval from 0 to 1 into 4 quarters. So what we have is on the left end point, notice that the left end point of the rectangle has to hit the function again. So here it's at 0, so this would be just essentially a straight line. From a quarter, it's a left end point, so at a quarter it's going to hit the function here, and we'll get a little rectangle here. Again, this is an underestimation. At a half, it's going to hit around here, and at 3/4, it's going to hit around here. Okay, so this is our region here, here, and here. Okay, so these are supposed to be of equal length, so it's not drawn to scale, but this is the idea. This is an underestimation, and notice that the space in between, compared to the previous examples when we had a half or just 1, they're getting smaller. So our approximation is improving. So let's go ahead and find the area of this region. How do we do that? Well, we essentially just we find the area of each rectangle individually and sum them up. This is our game plan. So the area, let's call it the A of the left end point. It's going to be, the first one's a distance of a quarter, and the height is 0. Okay, that's the first rectangle here. The second rectangle here, the distance, the width of it is a quarters, because from a quarter to a half, it's a distance of a quarter, or you can subtract a half by a quarter and you'll get the same answer. We just have to find the height of the rectangle. Again, the height of the rectangle corresponds to the height when the x of the function, when the x value is a quarter. So it's a quarter times f of a quarter. Let's put too many brackets. Let's put one bracket. Plus, the next one again is going to be a quarter. That's the base or the width of the rectangle. The height of the rectangle corresponds to f of a half. So times f of a half. And then lastly, let's continue, let's sleep on this side. We have a quarter times f of 3/4. Okay, so all we have to do now is plug in a quarter, a half, and 3/4 into our original function, f of x equals x cubed. So let's do that. F of a quarter is a quarter to the 3. This is equal to 1 over 4 times 4 is 16 times 4 is 64. So we get 1 over 64. If we plug in a half, so let's plug this in here. We get 0 plus a quarter times 1 over 64 plus, here it's a quarter. F of a half, let's just do this here, is a half cubed, which we saw earlier is an eighth, sorry, 1/8. And a quarter times f of 3/4 is essentially the same thing as what we have here, but on top we'll have 27. So f of 3/4 is equal to 3/4 to the 3. So 3 cubed is 27 and 4 cubed is 64. So we have a quarter times 27 over 64. Okay. Let's use a calculator and add these up. So we have 1 on 64 times 1 over 4 plus a quarter times an eighth plus 1/4 times 27 over 64. In total, I get 9 on 64. Okay, so this is the lower estimate, or the left end point of this graph. So we know it's going to be now 9 on 64. So before we had 1 on 16, now the approximation is 9 on 64. In decimals, 9 on 64 is about 0.14. Okay. Whereas 1 on 16, let's do this quickly, is about 0.06. So we're slowly getting closer to the true value. Okay, so the lower estimate here, let's write it up here. Now on our third attempt, it's 9 on 64, and let's go ahead and find the red end point, or the overestimation. Okay, so I'm just gonna erase this and we do the same thing. So for the overestimations, now we're working on this rectangle. We have a quarter. Now the right end point, since we're doing the right end points, it's gonna hit the function. So we hit over here on the green, it's slightly lifted. It's very thin. Here now the half, the rectangle is gonna hit the function. Something like this. At 3/4, around here, that's gonna hit the function, and then at 1, it's gonna hit up here. Okay. So again, it's clearly an overestimation. It's not perfect. There's a lot of error here because these parts of the rectangles are definitely above the function. But again, the smaller our widths become, the more, the closer we are to the actual true value. So let's go ahead and find the area of these rectangles. So the right end points, so area using the right end points, AR is equal to a quarter times f of a quarter. That's the height, f of a quarter. Then a quarter times f of a half. Plus a quarter times f of 3/4. And then lastly a quarter times f of 1. Okay. And these are values we calculated already. So a quarter times f of a quarter we saw was 1 on 64. Plus a quarter times f of a half is an eighth. We have it here. A quarter times f of 3/4 we saw before was 27 on 64. And a quarter of f of 1. Well, f of 1 is just plugging 1 into this function, so 1 cubed is just 1, so it's just times 1. So let's go ahead and solve this. Using a calculator, a quarter times 1 on 64 plus 1 on 32 plus 27 on 4 times 64 plus a quarter. So I'm getting 25 on 64. And in decimals, this is about, 25 on 64, about 0.39. Okay. 25 on 64. So we're getting closer and closer to the actual value. Yeah, this is about 0.39, whereas before 9 on 16 was about 0.56. So from 0.5 we went down to 0.39, so we're slowly getting closer to the actual value. Okay, so in order to get the actual value as close as possible, what's the smallest number we could think of? What's the smallest number that we could use? Obviously, if you take something that's extremely small, this would have a lot of rectangles and it will take a lot of time to do. But what's the smallest value that we know? Back from Cal 1, we saw that if you did advanced analysis, you would probably use epsilon. But without knowing epsilon, we have the limit as n goes to infinity of 1 over n. This is our guy, because we know this value is the closest number that we know right now after calculus 1, the closest value to 0. This is a very small number because we're dividing 1 by infinity, right? So we have a number that's essentially 0. It's not 0, it's really close to 0, so it's a very small number. So if we take the widths of the rectangles to be 1 over n, something that's extremely small as n goes to infinity, we'll get a very precise answer. Let's go ahead and do that. So here we partition the intervals so that the width of each rectangle is 1 over n. Okay, so we have to find the sum. We have to find the area of each of these little rectangles and then add them all up. That's our game plan. Then we're going to take the limit and take the limit as n goes to infinity because we're trying to make the partition as thin as possible. So let's go ahead and do that. I'm going to use right endpoints. There's really no difference. You can use right and left. You could do the left endpoint, and essentially it's a squeeze theorem argument, and you'll show that the right endpoint and the left endpoint, no matter which one you use, it ends up converging to the same value. So let's use the right endpoint, so AR, and we'll take the limit of AR. So we'll take the limit as n goes to infinity of AR. Okay, so we have the limit as n tends to infinity. And how do we find the area of this guy? Well, the first one here is going to be, well, the width is 1 over n, so it's going to be 1 over n times, what's the height? Well, since we're doing the right end point, it's going to be f of 1 over n, right? Plus the next one is a width of 1 over n, and if you slide over by a length of 1 over n, you're now at 2 over n. So it's f of 2 over n, plus so on and so forth until we get to the end. So it's going to be plus 1 over n times f of 1. Okay. So the next thing we could do is we could factor out a 1 over n, because each term has a 1 over n. Let's do that. And the f of 1 over n, remember the function that we're using is the function f of x equals x cubed. So we have 1 over n cubed plus 2 over n cubed plus dot 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 all the way to n over n cubed, or 1 cubed. Okay. And this we could rewrite as a summation. We saw this in the previous video. We could write it as the limit as n goes to infinity of 1 over n. This guy comes out. But in here, since we're adding all these terms, notice that the last term we could probably think of it as n over n. I think that's easier. 1 is the same as n over n. And notice that the denominator inside the bracket doesn't change. The exponent stays as 3. The only thing that's changing is the numerator, and it's going up by 1. So the way we could write this is the sum. Oops, not n. Too many n's. Let's use I. I equals the starting point. We're starting at 1, and we're going to finish at n. And notice that the only thing that changes is the numerator, so it's going to be I over, not n. Yeah, I over n, all that cubed. The exponent stayed as 3, the denominator was always n, the only thing that changed was the numerator, and it's going up by 1, so that's our index I, and this is equivalent to this, right? But what is this equal to? We could write this as the limit as n goes to infinity, 1 over n, and here we could cube the I and the n individually. So we have the sum from I equals 1 to n of I cubed over n cubed, right? So we cube each one individually. And since the sum only depends on I, we could remove the n, treat it as a constant. So we're going to pull the n cubed out, giving us the limit as n goes to infinity of 1 over n to the 4, because the cube combines with the n here. So we have 1 over n to the 4 times the sum I equals 1 to n of I cubed. And this, we have a formula for this that we saw in a previous video. The sum from 1 to n of I cubed is n times n plus 1 divided by 2, all that to the exponent 2, all that squared. So we get the limit as n goes to infinity of 1 over n to the 4 times n plus 1, all this divided by 2 squared. And now we could evaluate this limit. Let's go ahead and do that. Let me erase on top just to give myself some room. I'm just going to come up here. So what we get is the limit as n goes to infinity of here, if I expand it, I get n squared times n plus 1 squared over 2n to the 4. Okay. Expanding the n plus 1 squared, this is binomial, so you're just doing n plus 1 times n plus 1, which gives us n squared plus 2n plus 1. So here I could just write this as n squared plus 2n plus 1, and we could distribute the n squared, giving us n to the 4, 2n cubed, and n squared, right? And now, since the highest exponent of the numerator matches the highest exponent of the denominator, they're both 4, we could take the coefficients in front. Namely, on the numerator it's a 1, on the denominator it's a 2. So this is just equal to a half. Oh, sorry, this is a mistake. The 2 is squared, so this should be a 4. My apologies. This is a 4. Because the square attacks the 2 as well. So we have 2 squared, which is 4. So on the denominator, we have 4n to the 4, which is not a half, but a quarter. A half wouldn't have worked because we had to be smaller than 0.39. So this is a quarter. So the area under the curve here is actually a quarter. Okay. And this is how we answer the question, how do we find the area of a shape that has a side that's curved? So we treat it as a function and find the area under the curve using this. Breaking it up into little rectangles, finding the area of each rectangle and summing them up. So the previous example leads us to the following definition. The area A that lies under the graph of a continuous function, so we need the function to be continuous, which is f, is the limit of the sum of approximating rectangles. This is the idea. We find the area of each small red rectangle that we created, add them all up, and take the limit as n goes to infinity. That's what this is telling us. So a is equal to the limit as n tends to infinity. Delta x is the width of the rectangle, whereas f of x1 is the height of the first rectangle. Okay, so we're multiplying the width times the height because that's the area formula for a rectangle, and then we sum them up with all the other areas. Okay, taking the limit as n goes to infinity because we want the width to be as small as possible. This gives us the area of underneath the curve of the entire shape. Okay, so this is the idea. This is what we're using. We'll consider some more practice problems in the next video. For now, I just want to mention that the delta x, or the width, we assume the width of each rectangle to be the same. I'm going to continue using this assumption, but that's not a necessary requirement. We could have partitions that are of different lengths. So when I cut up my, when I partitioned my function, I used a half or a quarter widths which were exactly the same. If one is longer than the other, this is not an issue. What you could do is just take the limit. Instead of n goes to infinity, you could take the thickest one. So think of it as you're slicing bread. Not each slice of toast might be the exact same width, and that's okay. Just take the thickest slice of toast and make sure that that one's small. If all the other ones are smaller because you're taking the thickest one, then we can get away with this argument. So you're essentially just taking the limit as the largest, let's say, slice of toast goes to 0, making that one extremely small, meaning all the other ones have to be small as well. Okay, but to avoid complication, just for the sake of simplicity, we'll take we'll take the width to be of equal length. Okay, so I hope this video helped, and I'll see you in the next one.